talk and I'm streaming. I should be streaming in just a second. Okay, I think it's streamed.
Yeah.
Okay, I think it is streaming now. Awesome. Okay. I was honestly hoping that I wouldn't lead a discussion session today, but I guess that's not gonna happen. Okay. Give me 1 second. I hope this is the correct one, right? Yes, okay, that is the correct one. All right, hi, I'm Faye. Nice to meet you all. I haven't led this session before, but we do have a little more people than the morning session that I had, which is great. Awesome, let's start with a set problem. Let A be sets and U the universal set, given element-wise proof for the following. If A intersect B is A, then A complement to union B is the universal set. So where should we start? How do we prove that two sets are equal?
They're subsets of each other?
Yes, they're subsets of each other. Great, awesome. So let's start with that. So we want to show A complement to union B is a subset of U, and U is a subset of A complement union B, right? So that's what we want. All right, so where do we start? Element-wise proof. So how do we prove the first one? So this one.
We can do
use
something
substitution.
Okay, so I'm just gonna start. Let X be in, so element-wise proof, right? Let X be in A complement union B. We want X to be in U, right? But that's easy, right? Because if U is a universal set, anything that's inside of A or B or A complement would be in the universal set anyway, right? So then if X is in A complement union B, then X is in U, right? So that's easy. So that part is done. Therefore, the first part is proven. A complement union B is a subset of U. All right, let's do the other case. Let X be in A complement. Oh, let the X be in U. Where do we go from here? What do we do now? So let's draw a Venn diagram first for this problem. So we have the universal set right here, and then we have the condition that A intersect B is A, right? So that means A is a subset of B. So A is in here, and we have B here. That's how A intersect is A means that A is a subset of B. So what do we do now? We know that X is in U. We want X to be in A complement union B. So from this diagram, actually, what is A complement? A complement is this, right? So A complement actually includes B. So A complement union B is actually A complement. So B in this case doesn't actually matter too much based on the Venn diagram. So we're going to split into two cases. Since B doesn't matter that much, so we're going to split into the two cases where X is either in A or X is not in A. So X is an A complement. So this is like equivalent to X is an A complement. Does that make sense? Since from the Venn diagram, we know that B kind of doesn't matter that much. So we split into these two cases. So what happens when X is an A? Then we know X is in A intersect B, right? Because we have this condition that A intersect B is A. Right?
Hey, there's a question in the chat.
I thought B was A subset of A because the intersection of 2 is equal to A. If A intersect B, okay, so you mean like this? Then A intersect B would be B, right? Does that make sense? Yeah, okay, that's good. So we keep going. So if X is an A, then X is an A intersect B, since A intersect B is A, right? So then we keep going. Remember what we want is that X would be in A complement union B. So since X is in A intersect B, then X is in B, right? By the definition. Of intersection. Correct? Then the last part is just to say, by the definition of union, we have X is also in B union A complement. Any questions about this case? So this is case 1. So what about case 2? Case 2 is that if X is in A complement, right? Then this one is easy. We want to show X is in A complement union B. We can simply say then X is in A complement union B by the definition of union. Thus, U is a subset. U is a subset of A complement union B from the two cases above. And from here, you can write a conclusion that from what we've just shown, A complement union B is equal to U. I'm running out of space, but remember to write a conclusion. Any questions about this before we move on?
I kind of have a question about right above case 1 where you say if X is in U, then X is in A, or X is not in A. I'm kind of confused by where you came up with that.
So that's why I drew this Venn diagram over here, right here, this one.
Yeah.
So we have A as a subset of B, right? And then we have U as a universal set on the outside. So we kind of have to, like, my point is that what we want is that X to, so we want X to be in this, right? This is what we want. X to be in A complement union B. That's what we want, right?
Mm-hmm.
So, but the thing is that with this Venn diagram, we see that A complement union B is actually A complement. Do you see that? Like A complement is this whole thing. Union B, oh, actually union B would include this A part. But either way, it only has relationships to A. Like B kind of didn't matter.
Okay.
Does that make sense? Like it kind of doesn't affect too much the problem.
So is it like B is just a bunch of duplicate values that A already has?
Yes, basically. So that's why in this case, and then, you know, you kind of have to get a little creative with this type of stuff. Like you can try what happens if you say that if X is in B, right? Like, I mean, you're not guaranteed to get the correct answer the first time that you try something. Like there are multiple ways to think about this problem, right? If you say that if X is in B and then X is somewhere in here, right? X is somewhere in this larger circle, then there could be a possibility. You have to also discuss what happens if X is in A, or what happens when X is not in A, but X is in B. And what happens when X is outside, so outside of B. So like, if we draw this again, if this is A, this is B, this is U, then there are multiple possibilities, right? You can say that if X is in A and not in, if X is in A, like inside of the small circle, or X is in this middle part, where X is in this big part. If you want to discuss that, that wouldn't be wrong either. This is just the way that it's the easiest because B kind of doesn't matter too much, like for this specific problem.
Okay, and the picture that you came up with that A is inside of B is inside of U, is that from the like the instruction where it's A or not A union B equals U? Like
this is from here. This is from this condition.
Okay.
Yeah, because normally when you draw A, B, you draw it like this, right?
Yeah.
But then the thing is that A intersect B is A. That's what we know already, right? We know that A intersect B is A. So if you draw AB like this, A intersect B is this part, which is not A.
I see. Okay.
Right? So right. So because of this condition, you know A is a subset of B. Yeah, and then because of this condition, we have this part, because if X is in A, then X is in A intersect B. This is not always true in this case, right? This is not always true if A, like X could be in here and that is not in B. But because we know A intersect B is A, that's how we get this.
Okay. Yeah, I got that. I get that.
Yeah. Awesome. Shall we move on? So this is a set contradiction proof. Prove that these two sets have empty intersections.
One quick question. Are these questions like this? Is this what we can expect on the quiz coming up? Or exam?
Probably, because it's only gonna cover sets, and a Boolean algebra. So yeah, most likely I would say they're similar to the homework problems that you're doing. Is it right now or the last homework? I can't remember.
I think it was the last homework.
Yeah. Yeah, but hopefully, I don't know. Maybe there will be some easy ones, there will be some hard ones. It's not going to all be like really difficult and then you won't be able to get anything. And then we will definitely give partial credits for the quizzes. Okay, the second one, prove that these two sets have empty intersections. So, any ideas? What do you think? We have one side that looks like 2k plus 1. The other side, we have 4k.
Can't 4k be factored out into 2 times 2k, and so we can show that one is odd and one is always even?
Yes, so I think that is a perfectly fine proof. I would not take points off for that, but I don't know. Honestly, this is a little weird. I think that is perfectly fine for this class to show that, you know, by definition, this is odd, clearly. And then all of the elements in this set would be even because you can write it like this, right? And this would be even. Yeah, so then an integer cannot be both odd and even at the same time, so their intersection is empty. I personally believe it is fine to argue like that, but there is a more structured way of doing this. So if we actually continue on this path to show that one side is odd, the other side is even, what you can do to make this a little more structured is to show that both of these sets are natural numbers, right? So you can just say that, you know, by closure, we know that both of these sets include natural numbers. So first of all, show both sets contain natural numbers. And then you can show that if X is in the first set, X is not in the second set. So frame it in terms of like an element-wise proof. And then to show the other way around, to say that if X is in the second set, then X is not in the first set. And this should be structured enough to prove, to prove that there, you know, if it's in the second, it's not in the first. If it's in the first, it's not in the second. So there is no intersection. You cannot be in both at the same time. So I think that is a structured proof to show that the intersection is empty. It's an element-wise proof, just like what we've done so far. And there is another way. So kind of like, I'm just gonna write method 1. And let's look at another way. So this is kind of a more algebraic way of doing this. So we're going to prove by contradiction using this hint right here. So what is kind of the counter example? What do we assume? If we want to use proof by contradiction.
Would we just show that there's an intersection?
Yes, exactly. So that's what we assume. Assume X is in both. Assume X is in the intersection, so it is not empty. We assume that. So I guess there exists X such that X is in the intersection of the two sets. So then X has to satisfy two conditions, right? So X has to be this for some K in N, And we're gonna have to change another variable for the k because it is, because k, like the k on the left side and the k on the right side can be two different integers. So for some, let's say we use L for some L in natural numbers. So if X is in the intersection of these two sets, X has to satisfy both of these conditions, right? So X has to be 2k plus 1, and X has to be 4L for some L in N. So what does that mean? That means that 2k plus 1 is equal to 4L. So what do we do now? How do we reach a contradiction?
We just have to make them both. We just have to prove that they're unequal, right?
Or it doesn't have to be unequal. It just has to have some type of contradiction in it. It could be anything.
We
So
could do that even equals odd, right?
But that isn't a contradiction. So, right, okay. So this is like a little weird,
Well-
but go ahead.
I thought, isn't that what we just said before, that a number can't be both even and odd?
Right, but that is not a contradiction because you never assumed X to be even or odd, right? Contradiction is to say that something that you assume to be true isn't true anymore. That's a contradiction. We didn't assume X to be either even or odd.
But can't you just say that any number is even or odd? Isn't that just a fundamental truth of numbers?
Yes, that is true, but it is still, it's not as obvious as a contradiction because you didn't assume X to be either even or odd.
So should we make
Can-
a statement where we
Can we
assume?
just? Yeah.
I mean, if you
yeah.
want to try to split this up into two cases and say that, oh, if X is even, then blah, 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 then that goes back to method 1, right?
So how should we do it?
Right, okay, so let's keep going. So somebody, I think, said factor out a 2. Yes, so that is what we're going to do. So let me move the 2k on the other side. So subtract 2k on both sides, we get this, right? And then we can factor out a 2. So we have 2L minus k is equal to 1. And then we divide the 2 on both sides, we get this. And now do you see a contradiction?
Is it that the right-hand side isn't a real number?
Yes, it's not a real number. It is a real number. It is a real number, right? Real number is the bigger set. So the right-hand side has to be an integer.
Right.
Yeah, but the left-hand side is not. So that is a contradiction. But do you see what I mean? But like, this is something we assume to be true. We assume that L and K are both integers, right? Are both natural numbers. We did assume that. And then that means their difference should be an integer. That is something we assumed, and then we contradicted that by what we just did. Yes, so there's a question in the chat that says, where did integer come from? But then you subtract two natural numbers, you don't always get a natural number, right? Natural number doesn't have the property of closure when it comes to subtraction. And then also natural numbers are also integers, right? Natural number are just non-negative integers.
So could we have said that the right-hand side isn't a natural number and that is a contradiction? Or is 1/2 a natural number?
Wait, 1/2 is not a natural number. Natural numbers are the things that you can count. So 0, 1, 2, 3. Natural numbers are these. So
Right,
the
so
con-
instead, so could the contradiction be that the left-hand side is not a natural number?
the left-hand side is not an integer.
Right.
Yes. You like the point is that because this right-hand side, this doesn't have to be a natural number.
Oh,
It could be negative, right?
right.
Yeah, if it's negative, then it's not a natural number anymore. So then your contradiction that wouldn't make sense. Like the contradiction is that this has to be in Z, but then this is not in Z.
Okay.
Yeah, I should write it the other way around, like this. But anyway.
Still don't understand why you can't use the fact that 2k plus 1 is the definition of odd and 4l is the definition of even.
You can use that, but that wouldn't be a proof by contradiction. So if you go back to method 1, that is perfectly fine. But that is not a proof by contradiction. You have to assume something to be true and then show that something in there is not true, then you reach a contradiction. So you're saying something more of a proof by cases type of thing. You say that, oh, if I have an X, then it is odd and this happens. If I have an X, which is even, then this something else happens. It is still correct. You can still reach the same conclusion. It is just not a proof by contradiction anymore.
I thought that I guess that my thought process was if I assume that X is in both sets and then show that there is something fundamentally not true about it being in those two sets, then that would be a contradiction. Since that's what I guess I just misunderstood what a contradiction was then.
You're saying that if X is in the intersection, you show that X is not in the intersection.
Yes, because it couldn't be, because you're saying X is equal to 2k plus 1 and X is equal to 4L. But 2k plus 1 cannot equal 4L because they're defined as one being even and one being odd.
I mean, I think that would be fine too. I don't know. It's a little weird, honestly, because I think contradiction is a little more. It's a little weird, honestly. From my perspective, that doesn't sound like a proof by contradiction. I don't know why. But it would still be a proof. I believe that would still be a correct proof. Yes, but anyway, I don't know if that's enough of an explanation. Probably not.
It's whatever.
It would still be a correct proof. That is true. I do believe a lot of the times contradiction is like some little part in the things that you assumed is not true. That's kind of normally how proof by contradiction works. Yes, but what you were saying would still be correct. Yeah, I think the logic would still be true. Okay, let's move on to the next one. Let A, B, B sets prove that the power sets, intersection of the power sets is equal to the power set of the intersection. So we're doing the same thing, right? We show that they're the subsets of each other. Oh, I'm just looking at the question in the chat. It's like long, but okay. So prove that they're subsets of each other. So want to show this left side is a subset of the right side, and the right side is a subset of the left side. Right? Okay, so let's use element-wise proof again. So, but remember, the element-wise proof in this case, so an element in the power set would still be a set, right? Because the power set looks like it's a set of sets, right? So then, so C would be a set. Okay, so if we say that let C be in the power set of A intersect the power set of B, then C is a set. It's not just a number or something, it's a set. Just want to clarify. Okay, so if C is in the intersection of power set of A and power set of B, what do we know? Where do we go from here? By the definition of intersection, we have then C is in the power set of A. One second. C is in the power set of A, and C is in the power set of B. By the definition of intersection. Right? So where do we go from here?
What is
So-
C? Is C like an integer, or is it?
It's
nothing?
a set, right? So that's what I said. So this is a set because we're talking about power sets, right? So power set is a set of sets. So elements of a power set, an element of a power set would still be a set. All right, so the fact that C is in the power set of A, what does that mean? What is the relationship between C and A? Is C an element of A?
C is a subset of A.
Yes, exactly. C is a subset of A. So then we have, then C is a subset of A, and similarly, C is a subset of B. Right? So then, C, C is a subset of A intersect B. Right? Does that make sense? So if C is a subset of A intersect B, what is the relationship between C and the power set of A intersect B? So what do I write in the middle here? Yes, I see an answer in the chat. It must be in the power set. Yes, that is correct. So C is an element in the power set of A intersect B. So we have proved the first part, so from left to right. The intersection of the power sets is the subset of the power set of the intersection. So let's go the other way, from right to left. So we'll do the same thing. So let C be in the power set of A intersect B. Then what do we do?
Can we say that C exists in P of A and P of B?
Yes. So P. One second. Yeah, so P exists in,
But don't you say that C is a subset of A intersect B?
yes, that is a better way of doing it. So like then C is a subset of A intersect B. Then what happens? Remember by intersection? Thus, C is a subset of A, right? And C is a subset of B. Then C is an element in the power set of A. And C is an element in the power set of B. So C is an element of the power set of A intersect with the power set of B by the definition of intersection. Then we're done. So we just prove the other way. Nice. The power set of the intersection is the intersection of the power set, is a subset of the intersection of the power sets. Then you can write a conclusion statement. So you can say, therefore, since one side is a subset of the other and one side is a subset of the other, then they're equal. Any questions about this?
I have a small question. Is it important to make a distinction between C being an element of the power set of A intersect B and C being a subset of A intersect B? Like, to me, these are like very similar. I can reiterate.
Yeah, I don't really understand your question. I think what you're asking, so I think the important distinction is that the power set is a set of sets.
But C being an element of the power set of A and B implies that C is an element of A intersect B. It's this line right under therefore.
Yes,
like,
yes, but like,
Yeah.
what is your question about this right here?
I was just kind of wondering about that distinction. Like, is that an important step? Because I don't even, yeah. I don't know. Yeah, never mind.
So if C is a power set of a certain set, right? So if we don't consider this A intersect B thing, let's just say that C is in the power set of some other set, let's say like M set. Then C is a subset of M. Does that make sense to you?
Yeah, it does.
Right, okay, then that's the same exact thing. Instead of using M, we just have this in A intersect B thing, which is still a set. It's just written in a fun form, I guess.
Okay.
Yeah. Okay, we have a few minutes left. We can do this one. It shouldn't be very hard. So we want to use the Boolean algebra to prove that A plus B times B plus C is equal to AC plus B. So any ideas? What do we do? What is the first thing? So like, remember this is time, this little dot in the middle. It's just, yes, distributive. I see people are saying distributive in the chat, so that's good. How do we do distributive? Okay, so I will keep writing then. So B times, right, let's do this first. A plus B times B plus A plus B times C, right? So that's distributive. And then we're gonna do commutative to put it on the left side. Actually, strictly by let's like be very strict with the definition. So let's do B times B plus A. I think that is better. Yes. And then plus C times A plus B. So this is just by commutative, right? And then we can use this right here. So I think it's this one. So we use the absorption rule to basically say that this part is equal to B. And then we write this again. So this is by absorption. And we're going to distribute again, right? We have this C times A plus C times B. And then we're going to use commutative again. C. That's by commutative. So distributive commutative. And then we can use absorption again. So B, this right here. Would become B plus AC. And then you can do a commutative to say this is equal to AC plus B. Does that make sense? I think there's an easier way of doing this if we distribute the first step the other way around. So something like A times B plus C plus B times B plus B. I think this way is potentially easier. You can go try it out and see if it's actually easier.
Can't you reverse the distributive rule and take the expanded form to B plus A times C?
B plus A times C. Where is that step?
Well, isn't that just the distributive step, except for from taking it from the left side to the right side, you take it from the right side to the left side?
B plus A times C. Where, I don't understand your question. Like where exactly is that?
So it's the first step. You have A plus B times B plus C. And if you take that and go backwards from the distributive, like that's the expanded form to a simpler form.
Oh, yeah. I mean, you can, yes. I think that would be a lot easier. Yes, because they're equivalent anyway, right? You're saying like, you're saying this, right? You're going from here to left side, right?
Yes, that's
what you're
doing.
saying. Yes, you can definitely do that. Yes, and that's super easy, right? You just commute it again, and then that would be it. They're equivalent. You can use it one way or another. Yes, that's actually a lot smarter. I don't know why we have to go through, but yes, some people might argue that, oh, the distributive rule means that you're distributing from the left to right instead of the other way around, but they're equivalent anyway, and all the operations are commutative, so It is correct. Are we ending this at 45? Is that what it is? Slightly confused with the schedule.
Oh, yes.
Okay, yes, then that is the last problem we're gonna do. So we did include a few problems from quiz 2 in this discussion. So if you have questions about quiz 2 problems and you want some answers, I know some people were asking for answers for quiz 2, but we're not publishing the answers for these problems. If you do have questions you want to ask, you can either quickly ask now, and I'll give you some hints, or you can go to office hours for a more detailed explanation. But if you have no more questions, then that's it for today. Sorry for the really difficult beginning.
I have a quick question before you go, and I don't know if you like have time to go over it, but I was kind of wondering about set partitions. Like, I'm kind of bad at them, and I kind of need an idea of where to start, because I know that when you do a set partition, the first step is to like prove that it's non-empty or whatever.
Yes.
But when it's not like immediately obvious, like even or odd or something, I always like struggle to like prove a lot of these steps.
Just plug in a number.
But like, I can't plug in every number.
You don't have to plug in every number to show that they are non-empty, right?
Well, isn't the like the thing that like if it's like A and B show that like AB is a partition of C, do you have to prove that C is non-empty? Like, or that it's like not even non-empty, but like, because doesn't it have to be full or something? Isn't that like how set partitions work?
So wait, you're saying that, okay, one second. I think, so you're saying, I'm just gonna write it here. You're saying that show that something like A, B form a partition of C?
Yeah, where A and B are both sets.
Form a
And C is also a set.
Right, partition of C. So first of all, you show A, B are non-empty, right?
Yeah. So is that step just proving that neither of them are zero?
Neither of them are empty sets, not zero. So
Okay, they just at least have one value.
right, so that's all that you need to do, is that there has to be some type of a description for even and odd, like 2k plus 1, then all you need to show is that if that's say like k is in z here, you can just say that, oh, if k is 1, then 2 is in A, right?
Hmm.
And then if k is 1, then 3 is in B.
Mm-hmm.
First part is done. They're not empty,
Okay.
right?
And like you don't have to go all the way in, but like how would you prove that they don't have like that they're disjoint from each other, that there's nothing in common?
So that's the same thing as we just did, right? So so a lot of the times you just have to show that if there is an integer. So like C generally would have a description as well, right? So something here and then like K is in Z or something like that. So C has some type of a description right here, right? So
Right.
yeah, so a lot of the times what you want to show is just that I think a lot of the times you would use module arithmetic. So if I have something that's like 4, so this is kind of a bad example because this is obvious. You can just show that one side is even, the other side is odd.
Right.
like
That's
we
the
just
thing.
did.
Like all my examples that I reference are all like really obvious proofs for those.
Right. But then, oh, whoops. So if we have something that's more like 2k, and then like B is 4k plus 1, C is 4k plus 3,
Mm-hmm.
and then you want to show this is a partition of the integers,
Mm-hmm.
then what do? What do you think? How do you show that they're disjoint?
could you plug in some like arbitrary variable like x or something, and then prove that they're unequal to each other, or do like
No, you
Yeah.
can't do that, right? Because now you're not just showing that they're non-empty anymore. You have to show that they're a partition of Z. So that means you have to consider the entire set, not just an element in the set anymore,
right?
right? But then look,
Could you do a contradiction and
what
say
would you
that there's
contradict?
you could say that there is an element in both.
In all three of them?
Yeah, in all three. Or would
There
that be too
is
much
an-
work? I don't know.
Yeah, so, but then look at the descriptions. I think this is the most important part. Look at these things. They are 4k plus 1, 4k plus 3, right? So they're basically mod 4. You're looking at mod 4 type of integers, right? And based
Right.
on the division theorem, we know that for mod 4, an integer can be only represented in these 4 cases. Use what you've learned already, right? So this is what we know,
Hmm.
right? So then what do we do next? You see that the 2k would include these two sets.
Hmm. Wait, these 4 cases, this is all that it can be, mod 4?
Isn't that what we know already from the
I mean,
Um,
maybe, I don't know.
I mean, think about mod 4, something divided by 4, you're only going to have remainder 0, 1, 2, 3, right?
Right.
The fact that you have remainder 5 is the same thing as having remainder 1. You just divide by 4 again.
Okay,
Oh.
that makes sense.
Yes,
Okay, all right, thank you.
no problem. Yep, so that's how you show they're disjoint.
Yeah, sorry for going over time.
No problem. Who's the next?